Okay, we are being recorded. And listen, I'll go ahead and face you. Why don't I do that and get out of this black and white shot and get the, oh, that's Grandfather Mountain behind me. Yes, it is. Well, good morning. Okay, listen, one of the things I want to talk about, I'm going to switch real quickly away from my picture and do a problem. I want to do one from 4.8 that I will probably include on a quiz on Monday, all right? And it's got to do with, you're given a differential equation, and the solution to having a differential equation is to calculate what is y. You're given dy dx, and you're asked to determine what y is. And in this case, I'm going to give a boundary condition. So that means a point will be given that will allow you to determine what c is. When you do the initial problem, there's a general solution, means that there's a whole bunch of plus c's, plus a constant that could work for this. But by giving you a boundary condition, you can plug a couple digit numbers in and you end up being able to solve for c. I'm going to do one of those right now, okay? So I'm going to switch over to my iPad. And let's go. All right, so here's the problem I'd like to work through. And stop and think about what you would do to solve the problem, all right? Probably on a quiz Monday. I'm giving you dy dx. It's that quadratic. And given boundary condition. I could have given those as just being a pair of coordinates and a point, but that's the situation. That point is on the graph of y. Okay, so the first thing we've got to do, this is where we're in the section now, we're starting to take antiderivatives. And you've got to use, so the rules are going on here, and you got to apply them in this situation. This is a very basic polynomial, so you need to be able to apply them to other things, and we'll talk about that. I'll go, as we go through the class, I want to do some antiderivatives of other circumstances than just the polynomial type stuff. So the first thing we got to do is, we got to determine what y is. So I need to take the antiderivative of each term. Therefore, I'm going to walk through the steps and yet at the same time try to be efficient with it. And you should be practicing them enough now that you can recognize what to do here. So the antiderivative of 3x squared, we got to use the reverse power rule, so to speak, which is the 3's out front, raise the power by 1. I'll write that out again, divide by that new power. I'll condense it all when I make the next step, all right? Then we subtract. Again, there's no 1 there, but you know there's a 1. So raise the power by 1, 2 times x to the 1 plus 1 over that new power, all right? And then, again, when it's just a constant, sometimes it can be confusing because it's, and when it's 1, it's even more confusing. But if you had, what did you take the derivative of to get 1 is the question you've got to ask each time. And the derivative, so what you had to take was x. You took the derivative of x. So it's x to the 1 over 1. And officially, this is getting a general solution. You've got to include that there's some constant there. And then after we simplify this, we'll plug in the x and the y and solve for c, okay? So what do we have here? So we have y equals, the 3's cancel, we have x to the 3rd minus the 2's cancel, x squared plus the 1 cancel, and you get x plus c, all right? So if you're asked for a general solution, that's the answer right there. Because there's a bunch of different c's that would, if you took the derivative of this right now, you can check right now and verify, you'd get 3x squared, you'd get minus 2x, you'd get 1. All right, so that's that. Now, now we're going to solve for c. I'm going to plug in the y equals 1, and plug in the x, wherever it needs to be plugged in. And now you can see we got everything except for the c is the only letter in there, so I can solve for c. So I've got 1 equals 8 minus 4 plus 2 plus c. So that is 10 minus 4 is 6. So I end up with, this is 1 equals 6 plus c. So that means C equals minus 5. Therefore, don't get caught up in that, finish there and think that's your final answer. Remember, I had several people do that. That's not the answer. The answer is, what is the equation that fits this? All right? So the equation is going to be, you come back here, and you get y equals x to the third minus x squared plus x minus 5. And I will ask you on the quiz on Monday to verify it 2 ways. To verify that this is a correct answer. One, take the derivative. That means you'll have this. dy dx equals that. And we already checked that a minute ago and verified that's true. The other thing would be plug in the point and show that it works. So when x equals 2, 8 minus 4 is 4, plus 2 is 6, minus 5, you get 1. And that is 5 and 1 work there. So showing 2 and 1 work there. So that's showing your work for that, okay? So the final answer is this. Verify. Yes, dy dx, check, and 2, 1, check. Show your work on those. Make sure you show your work. Any questions on that at all? Did any other questions come up from section 4.8 in Sapling? Okay, let's go ahead on. I want to move on now to the text. The text shows some things in section 5.1. I'll tell you what, I've got a few slides that I want to show you. I'm going to go to a new share and go to this slide presentation, okay? And I'm going to kind of move through kind of briskly on a few of them because it's not essential. I want to just make a point and talk about what the main key point is from that section. But this is from the text now, section 5.1. So approximate the area under the graph of a function. And my section 5.1 recording that I put on there, if you have not had a chance to see that, go and look at it. Do it, watch it, because it's kind of important for what I'm getting ready to talk about with Riemann sums, okay? I'll talk about it, assuming I'll say something briefly about it, but not go into the detail. But the idea is you're finding the area of rectangles underneath the curve, is what you're trying to do. You're trying to find the area of rectangles and adding those up. We're also going to find the area of a graph of a function. So here's the idea I was talking about. What we had done was draw, and this drawing isn't quite accurate because some of them are above and some of them are below the function that's drawn here. But what we typically did was we drew rectangles below and drew rectangles above, and then came to recognize that as you narrow down the rectangles, the area that you have the discrepancy between the low and the high became less and less and less, okay? And so the circumstance is it turns out to then, as you go to 0, it fills in, it goes up smooth against that curve instead of having the corners sticking out of the rectangles and the space in between them. That's the main idea. So we're finding the areas of those rectangles and go from there. And I want you to hear this term, finding the area under the graph. What we typically did was this down here, we added up. Down here is where I'm looking right now. What we did was the delta x was how wide our intervals were. And in every case I did on the initial problem, they were all 2 seconds. And the height was determined by the left-hand side or the right-hand side of the rectangle. So each of the areas of those rectangles, all the areas were added up. And this is where the sum of these products, so this is the area of the rectangle, and you're adding them all up. That is where the sums come from. And this is where the sigma sign that this is where the integral sign that we use came from. Okay, this is a Greek letter sigma, meaning sum, and we're actually adding up a bunch of rectangles. That is what it's about, okay? It's meant to be like a reminder. Now, moving into section 5.2, I want you to see the name Riemann. It is a gentleman who gets credited with solving this way. And sometimes sometimes they call them Riemann integrals. And his name is attached to that in a good way. His picture's in the book. Riemann, a German mathematician, George Friedrich Bernhard Riemann. I believe it's Riemann. That's the way I've always heard it pronounced. But anyway, define the definite integral as a limit of Riemann sums. And what I was talking about a minute ago, the limit idea, is the limit as the rectangles get smaller and smaller, narrower and narrower and narrower and narrower. Okay? So that the sum of all those rectangles gets closer and closer and closer to the smooth curve as it approaches zero, as the width approaches zero. That's the idea, and that's why they call them Riemann sums. So if you ever ask for that, that's what it's talking about. And in some problems in the sapling, you're going to have to answer a couple questions, and they're similar to this. One thing I want to point out here, look at this slide now, is that when we stayed specifically with the width was 2 seconds every time, that was every rectangle. Okay, and then I said, well, if you cut it to 1, and then if you cut it to a half, et cetera, et cetera. Well, the actual definition, when you get down to the Riemann sum part of it, you look at this. This is kind of crazy, it doesn't seem. Doesn't necessarily have to be continuous on that interval 0 to b. Doesn't have to be non-negative. They're not necessarily equal. The subintervals are not necessarily equal. And you can pick any number in the subinterval. Doesn't have to be the left, doesn't have to be right, doesn't have to be the middle, okay? But the main idea is that as you get closer and closer to that width becoming 0, all of those variations aren't going to matter, okay? Because you're gonna hit something. The height is going to be, no matter if it's just 2 pixels wide, that is the height, all right? And the width is your x sub I, the difference, your delta x is the situation there, okay? So here's the main idea, right down here. The definite integral, they call it a Riemann integral or definite integral from a to b. The function is listed here, and this is indicating you pick some value u in the interval, okay? Again, first time through, we picked the low, then the high. Well, in this case, you can pick any interval doing it with Riemann, and the delta x sub I could vary. It doesn't have to all be the same. But notice this. So this is the width, though. Delta x is the width. This is the height. So they're all rectangles. And it's saying the maximum delta x sub I. So this could be a bunch of different sizes for what they're talking about. And the maximum is going to 0. So that means all the smaller ones have to go to 0 too. Got to be. So the idea is that's a Riemann sum. There's a couple questions in there that are going to ask you, if you've got this arrangement and this is cosine x, then what's f of x? The answer is cosine x. And that's the idea. It's just that this is the height of the function. Whatever the function is, that goes there. All right? Any questions at all about that? Again, I'm not going to be going into details on that. There's a couple of sapling questions that you'll have to remember that screen, so to speak, and just know that the f of u sub I becomes f of x when it goes over to the integrals form, the integral situation. Okay, so I'll tell you what, let's go back to that one more time. Let me point out this. Notice that this is the function. That is the height. That corresponds to this. This delta x, the Greek d, delta, is dx for us. Doesn't really seem to play a part in the calculation anymore because it's the extra, but it needs to be there. It's an important part. And in Calc 2, you'll need to make sure you've got that solid. So this is length, height, this is width, and it corresponds to this and this, all right? This a to b isn't necessarily going from 1 to n. This is how many intervals you're actually breaking it up into. So that's the key there. So like we had 5 intervals, 5 rectangles in ours. That would be 1 to 5 is what that would be. So it really didn't even have the a to b was in the consideration in that, right? Okay, so one of the things I wanted to point out, is that, notice this, existence of a definite integral. If the function f is continuous on the closed interval, so if it is continuous, then the definite integral exists. This is just existence is real. It's a real thing, bona fide. They talk about what bounded means. You'll talk about that more downstream in Calc 2 and other things, but bounded has to do with the y value that you get if you're on an interval and it's between, has a low and a high, then it's bounded, okay? If there's a lowest on the interval and a highest, then it's a bounded interval. And that is just a fact. I think sometimes that seems really obvious and overwhelming that people are stopping to say it, but it's an important part of some foundational things that'll be coming, again, Calc 2 more than this right now, okay? So let's look at this situation right here. I want to point out a reminder. Let me show you this. I've got this on the iPad again. I want to show you the idea that they're talking about here. Look at this. H is some constant. That's meaning it's a number, okay? So the idea is, and this is where we're talking about definite integrals. We're going to start doing a bunch of calculations. I'm going to do several examples here now, right? So one of the things I want to point to is this. Let's look at these. The one they give there is that one right, the bottom one is 1 to 4. But let's look at this. This is a constant, and they're saying if you're going from A to B, some interval that you're integrating over, remember what this is. This is area under the curve. H is a constant. Therefore, it's a horizontal line between A and B, all right? And I have an example up here. I'm going to do all three of these. I've got them on my iPad also, so I'll do those in just a second. You've got the answers there. But I want to show you this. Let's look at, I want to go to, let's stop share and go over to my iPad. Okay, so look at this first situation that I've drawn here. They had 1 to 4. 2 was the function going from 1 to 4. I'm picking from -2 to 3. I want to show you this, remind you this, that 2 is the function. That is saying, what are we finding here? Area under that curve. It's a straight line. 2 is, the y equals 2 is this straight line that goes forever in both directions. This integral sign is saying we're going from -2 to 3. So it's saying that we're going from -2 to 3. And what is the area of that region? So they've given as a theorem in the text that you take h, whatever h was, in our case it's 2, and multiply it times the difference between b minus a, right? So you end up with, in this case, this will be by the rule that they're saying, 2 times 3 minus -2, right? Which is 2 times 3 plus 2, which is 2 times 5, which is 10. And the logic of that is, what's the area of this rectangle? The area under that curve from 2 to -3. That's what that's saying. So if you've ever got a constant, all you got to do is take the constant and multiply it times the difference between A and B. All right? Make sure you do it in the right order, though. It matters. Okay, I'll talk about that again in a second. So the first example they gave in the book was the next question here. The integral of 2 from 1 to 4. The answer to that is 2 times 4 minus 1, which is, I'll bring it down here, 2 times 3, which is 6. Okay? And then this situation, notice this, they intentionally did this. Look at this, there's no number there, there's no constant. So what is that? This is a multiplicative arrangement, therefore there's a 1 there. There is a 1, all right? There's a 1, even though it's not written. So all you have is dx. That means the answer to this is going to be 1 times 6 minus -3, which is 1 times 6 plus 3, which is equal to 9. Okay? And that's the area, the other. And now look at this last one I want to show you and just draw a little picture to make sure you be mindful of it. I'm going to show you today, I'll open up in just a few minutes. I've got a couple other recordings that have to do with 5.2 and 5.3, and one of them is talking about the area when it's under the x-axis, okay? Under the x-axis is recognized to be negative. And that's something that we'll talk about, again, you'll be able to see that. I'll say something more about that in just a minute. But the idea is, and we always say the area under the curve, but when you get down below the x-axis, you come to realize it's the area between the function and the x-axis. And usually it's always above the x-axis. But when it's below, it's above, the area below the x-axis. It's the function up to the x-axis. So it's between. So the area of this function is the area between the graph and the x function. So we've got x equals -3. And in this case, it's not below. It's going from 2 to 4. And so it is this area right here. Okay? That's below the x-axis, so it ends up being a negative value. So what do we get? We get the constant h out front times the difference between 4 and 2. And that's -3 times 2, which is -6. So the area would be -6. And that could play a part in some functions where that number, a negative value, could make sense. And, with finance and economics, combination of different things in physics. But it depends on what you're talking about. If you're talking area, it doesn't totally make sense in a certain sense. But go from there. Any questions on any of those at all? Okay, let's go back to the slideshow and contend with right now. Fundamental theorem of calculus part 2 is the main focus we're going to be having. And it's this. If lowercase f is a function, it's continuous on the closed interval AB, if cap f is any antiderivative, notice it says any antiderivative of f, then the integral of lowercase f from a to b is the antiderivative of f, little lowercase f, it's cap f at b minus cap f at a. And the whole thing means that if you find the antiderivative, plug in b, and then plug in a to the same antiderivative and subtract them, you've got the area under the curve between these two values. That's the main idea, okay? So let's do it. They do an example here, and I've got several I want to do for you. And let me know if you've got questions on it, okay? So here's the situation. We've got, look at, this is x squared. Different. This is again, two numbers. The notation they use here is a little different than when I kind of came through math. It was more of a single bar. But the idea here is that you want to take the antiderivative of x squared. This is called integration. We're integrating x squared function. And that the integral of x squared from -2 to 4 is, okay, this is lowercase f. So you find uppercase f, which means raise the power by 1 and divide by that new power. Got it. And this step here is a step you write down the antiderivative and write down the values that you got to plug in for a and b. That's the standard mathematical procedure for doing an antiderivative, okay? So when you integrate, you write what the antiderivative of the function is from where to where, then plug in the 4 in here, that goes here, minus, plug in the -2 here, that goes here. And then simplify and get your final answer, okay? Now, notice what in the definition it says an antiderivative. Well, notice we didn't include plus c. So in the general form, there was a plus c, but if you're using the same functions, same circumstance, then the plus c is the same for this function as it is for this function. So when you subtract, you are getting the same c, so the c's cancel anyway. They're gone. So you don't have to. When you're doing a definite integral, you don't have to include plus c. It's automatically taken care of. It's wiped out in the process of doing the problem, okay? So notice this one, an antiderivative, that's, yeah. Now look at this one. The antiderivative of cosine x dx from 0 to pi over 3. What is the antiderivative of cos? What did you take the derivative of to get cos? Sine. So the answer here is sine, and the value of A is 0, B is pi over 3. So write the notation there. I'm going to do a couple of other problems myself, and when I do it on my iPad, I'll use my old form, and that's not using the double bracket. So whatever way, I want you to write something that denotes what A and B are, though, okay? So then you plug in B into this function, boom, and you plug in A into this function, boom, and calculate. Sine of pi over 3, you can remember that's 180 over 3, so that means it's 60 degrees. 60 degrees is the 30, 60, 90, 30, it's the 30, 60 arrangement. It's either 1/2 or square root of 3 over 2, the sine and cosine. This is sine, so it's the y value. 60 degrees is higher. Therefore, it's the square root of 3 over 2. This is square root of 3 over 2. And the sine of 0 is 0. So we get the square root of 3 over 2 minus 0 is square root of 3 over 2. Okay? Questions on that at all? All right, what I'd like to do is go through several problems now. I want to come back to this in just a minute and talk about what that next screen was discussing. But first, I want to go through several problems with you. And let's go to my iPad. And let's go to a new screen. Let's do several. And there's variations on this theme now because you can have negative exponents, okay? Let's go through these. Let's go. I've got x squared. They just did x squared on the computer there, all right? So on that screen. Let's now do, they did cos also. So let's do this one. Let's do the integral of 1 to 3 of 1 over x cubed dx, all right? If it's up on top, then you just add 1 to the power and divide by that new power. Well, before we do that, we've got one in the denominator here. I've got to rewrite this and get this in the form to the -3, right? So that's a little bit of a special case. So everything else stays the same right now, but this is x to the third, -3 dx. Okay? So now the next step, notice what's happening. I am integrating now. I am finding the antiderivative. So the antiderivative bar, that s out front, goes away, and the dx goes away. And all I have left is the antiderivative of this function. So what I end up with is I've got to raise the power. I don't put the bar or the dx. I raise the power by 1 and divide by that new power. -3 plus 1 is -2. All right? And the notation I said I'm going to use is just a bar that says it goes from 1 to 3. I guess that could be confusing sometimes if you have more than one term. It's make sure you know, if you have parentheses around it, if you got more than one term or something, but in the book, they just had brackets around it or the way they use in the text. So this becomes, let me rewrite this one more time. I end up with, that's x to the -2 over -2 from 1 to 3. Well, let me fix that. Let me simplify that a little bit more. I get, that's 1 over, and it's a -1 because the negative is on the bottom with 2. So now I've got x, 2x squared on the bottom. The 2 stays down there. It's negative, but that's a negative sign out front. This negative exponent, this -2, causes the x to go downstairs with that 2, okay? Down with the 2 that's already down there, and the minus sign we usually work with, it's either out front or up top, so that's what we've got now. But that is from 1 to 3. And now I've got to plug in 3 first and subtract plugging in 1. So I end up with minus 1 over 2 times 3 squared, right? That is f of b, cap f of b, minus cap f of a is, now I've got the minus sign that comes with the formula, right? I've got cap f of b minus cap f of a. I need that minus sign is there as part, so this minus sign on the term here has to show up in there. So I've got minus 1 over 2 times 1 squared. All right, that now equals -1 over 2 times 9. Minus a minus is a plus, 1 over 2 times 1. So that I end up getting minus 18, minus 1 over 18, plus let's get a common denominator. That's going to multiply top and bottom by 9. So I end up with plus 9 over 18, which gives me 8 over 18. I'll ask you to simplify, which means that it looks like 2 goes into both of them, so that equals 4 over 9. Now, pull out your calculator if you got it. Let's do that. You can check the answer right now on your calculator. We got 4/9. So what the calculator going to say? It's probably not going to say a fraction right away, so it's going to be the decimal, which should be 0.44444. And then we can verify it by hitting the key that they talked about on that. They talked about it on the YouTube about how you can check what the fraction is. So let's do this. So I'm going to go. I'm turning it on. I've got Math 9. Again, I'm in TI-83 mode right now. So I've got FNINT. The function name is 1 divided by, so what I've got is, on my screen, is this. And now I need to plug in, I'm going to plug in just like it is. I'm going to do I'm going to do x to the 3 like it's written, okay? And then I'm going to, my next term is going to be what's the variable of concern, and then I've got a and b. So on this, I'm going to do that. You've got it in position. If you got a TI-84, you just plug it into the integral that shows up when you push Math 9. So I'm going to do 1 divided by x cubed. Don't need parentheses on this because it's just one term, minus x to the 3rd. Okay, and then I've got x, comma, 1 comma 3, close parenthesis, enter. 0.444444. And now if you hit math again, if you hit math and hit enter, that means you're selecting frac. Number 1 is frac. So if you either push 1 or hit enter, and now hit enter again so that it'll actually do the calculation, it converts it back to a fraction as 4/9. Okay? Questions on that at all? Okay, let's do another one. Let's do one we haven't talked about yet, okay? And that is, what if we have a fractional exponent? All right, so what if we have the integral, and I'm going to also change it to, let's do this one with x. I'll say 0 to 1 of the square root of x dx. All right, what do you do? Yes, it's just like when we started doing fractions with taking derivatives. You gotta think +1 - 1 of a fraction. That's the part of the situation. So first we need to rewrite it. 0 to 1 x to the 1/2 dx. So using now also fundamental theorem of calculus. In the sapling problems, they say using the part 2 of the fundamental theorem of calculus. That's saying do it by hand, okay? So if you can check it on the calculator yourself, your answers every time. But if it says using part 2 of the fundamental theorem of calculus, that's saying do it by hand and show your work. I'll be asking you to do that on Monday, okay? So this becomes now, all we got to worry about, the integral bar goes away, the dx goes away. I've got 1/2 plus 1. Again, I'm going to rewrite it as a fraction with the same denominator, divided by this new fraction, which is going to be, I can see it's going to be 3/2. Okay, and this is going to be between 0 and 1. Now, and notice you guys, equal signs, some of you still are idle and not including equal signs. I'll have the test then finished up for you by Monday for sure. But it is a matter of making sure you need to use equal signs as part of mathematical statement, okay? Mathematical equivalent. So now this becomes x to the 3/2. And the 3/2 on the bottom, if we flip that and multiply, we end up with 2 on top and 3 on the bottom. And this is from 0 to 1. All right? And now, if you have it in your head what that 2 in the bottom means and the cube means, that's fine. If you don't, then we do need to recognize that this is 2 the square root of x to the, remember the 2 is the root and the 3 is the power that's on the exponent on the variable divided by 3 from 0 to 1. All right? So now that becomes, so if I plug in 1, I get 2. You can see that that's going to be 1, right, over 3. And this becomes, then we got to subtract 2 times, okay, and you guys will know that when you know it's 0 and you can see that the whole thing is 0, then you don't have to write everything out, okay? Sometimes a single term inside there will become 0, but the rest of it won't. So you got to be conscious. Just because there's a 0 there doesn't mean the whole thing is sometimes. But in this case, the whole thing is 0. If the numerator is 0, then it's got to be 0. So this turns out to be, you can see that that square root of 1 is 1. So I end up with 2/3 minus 0, which is 2/3. All right, really quickly, do this on the calculator. Let's verify that it's right. I'm going to go to Math 9. And I'm going to do the integral. I got it. Okay, I'm going from 0 to 1 of the square root of x. So I'm going to put literally the square root in here for on 9. So I got second square root of x. You could put x to the 1/2 if you wanted to, but that's kind of, that's fine if you know it's right. That's the square root of x. And then I've got, what is the variable of concern? X. Going from comma 0 comma to 1. Close parenthesis. Answer 0.66666. And if I hit math, enter, enter again, oh, you know what? I found this happened yesterday too. On my calculator, when I did this, I don't get 6666666. And I'm not sure exactly what happened there. It's got a little rounding error here. I've got 1, 2, 3, 4, 5, 6 sixes, then I've got 877. So got to be careful. This is 2/3, you know, is the correct answer. And this somehow got a little rounding error in the process. So it didn't come back with a fraction, 2/3, because it has that 877 in it. I wanted to note that. So the flaw, the limitations of how many places does the decimal go out in our answers on this calculator, and there's limitations that happen with that. Questions on that one at all? Okay, let's do another one. This time, let's use a different variable. I'm gonna do it on the same page here. I'm gonna do the integral of 1 to 8. Check this one out, please do it with me. The cubed root of y, and notice what the variable of concern will be, dy. So the mathematics of this is gonna be y on my sheet. That's the variable of concern, that's the independent variable. So on my calculator, I've got to plug in x, but I've got to be conscious that they're giving me a y in this problem to solve. So if anywhere I've got to denote it, I need to use y for my final answer, okay? But in this case, it's going to be a number. Anytime you've got a definite integral, you guys, where a and b are given, the answer should be a number, okay? So notice every time there's a value that shows up. So let's do this problem now. If you want to change these to x in the process, feel free, but remember the problem was given in y. I'm going to keep y all the way through and just do it in my calculator differently. So this is the integral from 1 to 8 of y, what's the power? Yes, I heard the hum. It's 1/3 dy. So what do? Integrate. Bar goes away, dy goes away. I end up with y to the 1/3 plus 3/3 over the new exponent, which is 4/3. And that's going to go from 1 to 8. All right? Questions? So the next step. So what do we have? We've got y to the, I'm going to simplify this first, y to the 4/3. And I scrunched over again, and I got to flip and multiply that 4/3. So the 3 is going to be on top and the 4 is going to be on the bottom. Okay, and this is going to be from 1 to 8 again. And now, you know, a variety of ways. If you recognize that's a cube root, you can do a step in your head, whatever, how you want to do it. But I'm going to go ahead and write it out. This is 3 the cubed root of y to the fourth over 4 from 1 to 8. Okay, so there's different ways to look at this. One of the things, the way to look at this is to rewrite this top the way I did the radical. What I'm going to do is I'm not going to take a to the fourth and then take the cube root of that. What I'm going to do is take the cubed root of 8 first, because I know that's 2, and then take 2 to the fourth power. All right? So what I'm going to do, how I'm going to write that then is like this. So what I'm really doing is taking the cubed root of y and taking that to the fourth power. Same thing. That is y to the 4/3 power. Okay? So what I'm going to do now is plug 8 in. So I've got 3 times the cubed root of 8 to the fourth over 4 minus 3 times the cubed root of 1 to the fourth over 4. And I hope you can see that you don't have to do every one of these steps. You can see right now that that top number is 1, okay? It's going to be 3 times 1. At first, you might want to do it to make sure your thinking's correct and everything, but that's 3 times 1 on top. Okay, and let's do the next step. What do we have now? So the cubed root of 8 is 2. So I'm doing every step, just every step of the way, because this is what you need to do in your head mathematically. You got to do these steps. Even though you writing it out, you could be more condensed. This is going to be 1, the whole thing. 1 to the fourth is 1. I don't need that to the fourth. I could put it, but let's just stay consistent. Over 4. So now what do I have? I've got, this is 3 times 16. That's 2 squared is 4, and 4 times 4 is 16. So that's 2 to the fourth is 16 over 4 minus 3 over 4. So notice here, I'm going to have to subtract with the denominator of 4. So I could cancel the 4 and the 16 and get an integer number, but I'm going to have to combine them anyway with fractions. So I'll just leave it as a fraction. So that's 48 over 4 minus 3. So that equals 48 minus 3 over 4, which is 45 over 4. And on the calculator, what did that turn out to be? That goes into there, what, 11 times 11 and 1/4? So I got 11 and 1/4, which is equal to 11.25. Let's do it on the calculator. Verify we get that, 11.25. So I'm doing math. Do it with me now. Get your calculator out, please. Do math. 9. And our function is the cubed root of y. So I'm going to use x, okay, on the function. So I end up with, I'm going to do y, x to the, and now up there, it's kind of important on the exponent that the way I've got it on mine, I'm doing it in a horizontal line, okay? I'm not doing it up on the integration bar. If you got it up there, you can just do 1/3 up there. I've got to do parentheses 1 divided by 3, close parentheses, because x to the 1 is x divided by 3 is x over 3. Well, that's not what I want to do. So I'm going to do comma, variable of concern is x, and we're going from 1 to 8. 1, comma, 8, close parenthesis, 11.25 on mine. Crowd on fire? Any questions at all? Okay, so I wanted to do that one was a fraction. Okay, let's do 2 more. One in particular, right now, let me get a clear screen. And this one is section 3.3. Okay, derivative of, okay, what do you do with this? 0 to 1 of 1 over 1 plus x squared dx. Okay, and what is that? What did I take the derivative of to get that? You've got to have in mind that there's this inverse trig functions are out there. Inverse sine and inverse cos. So it's possible I could throw one of those in there on the quiz just to keep you focused, okay? Because the automatic thought is if you rewrote this, this has got a function in the denominator. There's a way to solve this using trig, but, using calculus, But the idea is you need to recognize that this is the idea that if you have y equals inverse tan of x, y prime is equal to 1 over 1 plus x squared. You talk about excitement, all right? And so the situation is that if you've got this to start with, that this is equal to then the inverse tan function, or you could say arctan is sometimes how it's written, of x from 0 to 1. All right? So that gives us inverse tan at 1 at x at the y value is equal to 1, and we've got minus inverse tan at 0. All right, now you got to get to some trig stuff. Where is tan? Tan is sine over cosine. Sine over cosine. When tan is 1, sine over cosine is 1. That means sine and cosine have to be the same. That's happening at the 45-degree angle marks. And it's positive, so the main one it's going to talk about is at 45 degrees, which in radians is called, it's not, pi is 180. Pi over 2 is 90. And half of that is pi over 4. So this turns out to be pi over 4 minus, and what angle is the tangent 0? Sine over cos. Sine is 0 where? 0. 0. So the answer is pi over 4. Now do this on your calculator and see what, I didn't look at this one on my calculator. So pi over 4 should turn out, notice what, I didn't write 4 on the denominator there, did I? I got pi over pi. What is that? Pi over 4. Okay, so let's see. So I'm going to do math 9. Let's verify what happens on this. Math 9, I've got 1 divided by, parenthesis on mine, 1 plus x squared, close parenthesis, comma x, comma 0, comma 1, close parenthesis. The answer is, does that look like pi over 4 to you? Well, let's see, 3.14, yada, yada, a little bigger than 0.75? That sure does. What I'm going to do in my next line, if you ever run into a situation like that, you have a hunch it's got something to do with pi, let's type in pi divided by 4 and see if what I get. Pi divided by 4. Looks familiar? Yes, it's exactly the same thing on my calculator, okay? So that is that situation, okay? So that one is inverse sine. Inverse sine is another one that you've got to work with when it's 1 over the square root of 1 minus x squared is another deal. One other one we haven't done yet is this. Let's check this one out. The integral from, let's go -1 to 0 this time. Notice that's left to right on the number line still. But let's do e to the x, just for fun. In terms of x, all right? So what do you do? What do you do? So what we do is, what's the antiderivative of e to the x? Yes, I heard you. A couple of you just mumbled it softly. That was nice. So we get e to the x from -1 to 0. All right? So now the number on top goes first. So I've got e to the 0 minus e to the -1. Let's rewrite that. That's equal to 1 minus 1 over e. So if you're asked for an exact answer, bingo. Let's calculate that on our calculator and verify what we get. And 1 minus e will be one thing. Let's do that first. I'm going to do 1 minus 1 divided by e, second division sign, right? I get 0.632, rounded to 3 places. I get 0.632. There's a bunch more. Let me write it out. 1, 2, yada, yada. Okay. And now let's do the integral from -1 to 0 and see what we get. So I'm going to do I'm going to do math 9. Math 9. I've got e to the x now is what's going to come next. So I've got second natural log, and I plug in an x there and close that parenthesis off, comma, e to the x is what needs to go in the function position. It's dx, comma, -1, comma, to 0, close parenthesis, enter. 0.63212, yada, yada, yada. Exactly the same thing, okay? Any questions on that? Anybody? Anybody get something different you'd like to talk about that? Okay, well, listen, section 4.4 is talking about, I'll tell you what, yeah. Well, section 4.4, 5.4, excuse me, is talking about a bunch of different rules that you use in when you're doing antiderivatives, when you integrate. And some of them are that if you have two integrals right beside each other going 1 to 2, and the next one's going 2 to 3, let me say this. So if I have going from 1 to 2 of x squared dx, and I go add that to the integral 2 to 5 x squared dx, you notice that if you did these together, notice this one starts at 1 and goes to 2. This one starts at 2 and goes to 5. So the whole thing will be, the answer will be the same as 1 to 5 x squared dx. Okay? That, I hope you can see, is pretty factual. The area under the curve, you add those two areas together, you get the whole thing. Another one that they show is this, that if you have, if I go 1 to 2 of x squared dx, that's equal to, if I go 2 to 1 x squared dx, it's going to be the negative sign of it. It's going to be the negative of it. So you stop and think about what this means. That means this problem right here means I've got cap f of 2 minus cap f of 1 is going to be the answer when I do this. Well, what I've got here when I switch them is I've got 1 on top, so I've got cap f of 1, whoops, cap f of 1 minus cap f of 2. So it just switches them. You're going to get the same difference, but it'll be the opposite sign, whatever it is, okay? So if you switch A and B, it gives you the negative of whatever you had for the original, okay? That's a biggie. Now, there's one last thing I want to talk about because it's going to come up in section 5.5. I'm going to include it on this exam, a very brief question, and we'll do more on it on Monday. I'll talk about this more in depth, but I want you to be able to look at this and get familiar with it, okay? Hey, make sure you do the practice problems in 5.3. There's a bunch of them. There are, and as a result, it's meant for practice, you guys. There's 22 problems in 48. And 5.1 has 9, 5.2 has 9, and 5.3 has 12. Make sure you hit them. Come in Monday with questions that you're uncertain about. This is finishing the semester, you guys. You got an opportunity now. Get a strong grade on this test and nail this final. And you're going to have an affect the grade in your course in a real wonderful way. Your understanding will be strong too as a result. But here's the key point I want to make. Let's go to a new screen, and this will be the last thing for the day, okay? So what I want to talk about is when you have to use the chain rule, okay? All of ours so far when you're taking the antiderivative have been one term, all right? Well, what if you have to use the chain rule on something? Let's look at the situation right here. If I have the function y equals sine of x to the third power, all right? Look at what I will get from this. I've got to use the chain rule. I got a function inside the other function. If I'm finding the derivative, I've got dy dx, or I could use y prime, equals, okay, I take the derivative of the outside. Derivative of sine is cos. So I get cos. I rewrite the x to the third. And then I got to use the chain rule. I got to multiply by the derivative of x to the third, which is times 3x squared. Okay? So look at what that's going to look like if I'm taking the antiderivative of something. If I've got this, and notice there's no a and b on this, this would be called an indefinite derivative, indefinite integral. The other one was definite because you had a and b. If you don't have them, it's called indefinite. But you have, if I had 3x squared cos x to the third dx, on this integration, look at this now. This looks a little bit of a monster. You know what I mean? But if you can, this is where you do a substitution. This is called substitution. Notice if you've got two things to be concerned about, two functions here and here, and one is the derivative of the other, or a common multiple, a constant multiple of the other, then we've got x third. Well, the derivative of that is 3x squared. So in this simple case, because it's exactly what we need, if I said u equals x to the third, then du is equal to the derivative of this, 3x squared, and you need to start including the dx whenever you do one of these substitutions, okay? We'll practice this again. I'm going to introduce this again, go through it on Monday, and be solid with it. But here's the idea. Now what I do, this simplifies the problem incredibly. Look what happens. Now I get the 3x, I get the x cubed is my u. So I've got the integral of cosine u, and 3x squared dx is what I've got left. I could rewrite this as a different order. Cosine, sometimes you might want to do that at first just to make sure you've got it exactly right. Put those over there together, okay? Well, this is my dx. So, excuse me, that's my du. So this is this cosine u du. Now, what's the integral of cos, period, of what's cos of x, or cos of u? Now the answer is sine. So you end up with, this is equal to sine of u plus c, all right? Because it's a there's no, we didn't have any, we had to add a plus c. Notice what we started with. Now you resubstitute. Don't leave the u in there. The original problem was in terms of x. You need to finish in terms of x. So it's going to end up being, I substitute back in my u, I get sine of x cubed plus c. So the integral of this mess turned out to be this because of that, all right? There's other situations that are going to come with that. I want you to just see it. Thank you all for being here. Those that aren't here, I hope they'll watch the video and the tape and be able to see that. That's coming next week, and it'll be on the last exam, and it'll be on the final, okay? But for right now, do all the problems from 5.3. Hit all of those using the fundamental theorem of calculus. Writing out and then verifying on your calculator the definite integrals, what all the answers are. So hit all the 4.8. I'm going to ask you on the quiz a differential equation problem. I'll probably ask you one of these, possibly, but I'm definitely going to ask, no, you know what? I won't ask one of these. On the quiz, I will ask you to use the fundamental theorem of calculus and show your work on calculating the definite integral, okay? So those for sure will be on there. Any questions right now about anything we've done so far? Well, that's all I have, you guys. And if you've got something else, I'm going to go over to the Zoom office hours. And if you want to come over there, you're welcome. Again, it's at the top of the top box. And as you learn, if anybody has any other questions, I'll leave slowly here. You've got opportunity to get it. I'm going to stop recording.